Hello everyone, welcome to my channel Quantum Pinguino. Today we're going to be discussing something called elementary cellular automata, which I found quite interesting. I'll start from the basics and then work my way up to talk about some of the more mathematically unique cellular automata rules, and also show some plots showing some of the cooler patterns. To produce these plots, you can click on the link in my bio, which takes you to my GitHub page that has the code I use to make them. So cellular automata are these mathematical models that live on n-dimensional grids of cells, and each cell can occupy a certain state. The most basic configuration of a state is 1 or 0. The cells on the grid evolve based off something called a rule. For a given discrete time step, a rule determines how the state of a certain cell will change based off its current state and the state of the neighboring cells around it. All we need to provide a cellular automata is its initial configuration and a rule, and then we allow the grid to evolve on its own over time. The most popular example of cellular automata is in a two-dimensional grid called Conway's Game of Life. You can make interesting patterns like the one shown below, where you can make these little objects shoot out what are called gliders. So elementary cellular automata are a specific type of cellular automata where we work on a grid of a 1D array of cells of a length n, which is taken to be greater than or equal to 3, and each cell in this grid takes on a binary state, filled versus empty, 1 versus 0. The rules that we use to evolve elementary cellular automata have been standardized by Stephen Wolfram into something called the Wolfram code. To derive a rule, you take a number between 0 and 256 and convert it into binary, padding it on the left so that the number has at least 8 digits. After converting into binary, you match each digit in your binary number to one of the patterns. Now, the orientation of these patterns is fixed. This is what's called the Wolfram code. So in the 2 to the 7th place, you will always have 3 black squares, and in the 2 to the 0th place, you'll always have 3 white squares. What these 3 squares represent is a given cell and its 2 adjacent neighbors. So this means that if we see a pattern in our current generation of cells, which is 3 white squares, then for the example shown for rule number 30, since the 2 to the 0th place has a 0, 3 white cells will get mapped to another white cell. However, if we see a pattern of 2 white squares and 1 black square, then since the 2 to the 1's place is a 1, this means that this pattern will map that cell to a black square. So since this may be hard to visualize, I made this short example with a grid of size 5 and our earlier example rule 30. So for the first cell, we see that the cell to the left of it, since we're using periodic boundary conditions, we have to wrap around the entire grid to the other side to get the white cell. Then the current cell is a black cell and the one to the right is a white cell. This pattern maps to the pattern shown in the Wolfram code for position 2 to the 2nd, which is a 1, which means that this original black cell in the first position will be mapped to another black cell. The second cell is more straightforward since we don't have to worry about the boundaries, and we can directly read off the grid that it's just a black, white, black pattern. This maps to the pattern in the rule for position 2 to the 5, which is 0, so the second cell gets mapped to a white cell. We follow the same procedure for the third cell, which is a pattern of white, black, black, which is in the position 2 to the 3rd, which maps to a black cell. And then in the fourth cell, it's a pattern of black, black, white, which maps to the pattern in position 2 to the 6th, which is a 0 mapping to another white cell. For the fifth cell, we see it's a pattern of black, white, and then we have to wrap back around to the start of the grid to get another black cell. This corresponds to the pattern in position 2 to the 5th, which maps this fifth cell to a white cell. Finally, we have our full second generation, fully evolved from the first generation, following Rule 30 and the Wolfram code. And to reward ourselves for iterating our first cellular automata, here's a short clip.
Muchas gracias, afición. Este para vosotros.
Now that we have a general understanding of elementary cellular automata, let's play around with some different rules using the Python script that I wrote that you can find linked in the bio of this video. One interesting property of elementary cellular automata is amplichirality. Amplichirality is the idea that for a given rule, you iterate it a certain number of steps. For example, on the left we have rule 110 iterated 50 steps. And if you were to reflect this image on the y-axis, you would see that this image is produced exactly by another rule, in this case rule 124. We call rule 110 and rule 124 to be mirrored elementary automata, and they have a property called amplichirality. 64 of the 256 rules are actually amphichiral. Elementary automata can also have complementary rules, These complementary rules are equivalent to replacing every black square with a white square and every white square with a black square, essentially taking the negative of an image. Here we have this for Rule 110 and its complementary pair, Rule 137. Only 16 of the 256 rules are complementary. Also, a keen observer would note that it's not a one-to-one mapping. We can see that the mirrored image in Rule 137 is slightly offset from Rule 110. This is expected as we don't expect an exact one-to-one mapping depending on the initial conditions and the exact evolution of each rule. The last transformation property of elementary automata we'll look at is essentially combining the last two, looking at mirrored complementary pairs of rules. For Rule 110, this is Rule 193 and is equivalent to flipping over the y-axis and also taking the negative of the image. Again, it's not an exact one-to-one mapping, and only 16 of the 256 rules are mirrored complementary. Now, getting into some of my favorite rules, we have Rule 60, which can be modeled using Sierpinski triangles. Essentially, if you go row by row for each iteration, we have the first row is one black square, so in binary 1 is 1. The second row has two black squares, so in binary you can read this as 1, 1 equals 3. Third row has one black square, one white square, followed by another black square, which becomes 1, 0, 1, which is equal to 5. And you continue this pattern, which gives you the pattern which models Sierpinski triangles. And these four images are the same rule, just with different iterations to see how the size of the triangle evolves. And you basically get this kind of fractal pattern that emerges. Another cool rule is rule number 30. So each iteration of the rule is obviously deterministic. If you know the previous row's configuration, you can determine the next row's configuration. However, there are some rules in the elementary cellular automata which essentially don't have a set pattern that you can observe. For example, you can see the pattern of triangles emerging in the Sierpinski triangles and can predict easily mathematically what the next one will be. However, there doesn't seem to be a set pattern for Rule 30, and we call this deterministic chaos. This also means that it's very sensitive to the initial conditions. Where you put the black square, how many black squares you put, what the configuration is, can all lead to vastly different outcomes. Finally, we have what in my opinion is probably the coolest rule, which is Rule 110. Rule 110 is actually something that's called Turing complete, which means that you can encode information to store and retrieve data as you wish, in addition to encode logic gates such as OR and AND. And you can use Rule 10 essentially as a traditional computer to perform any logical function you wish. Of course, this may be a bit more difficult than it is on your at-home computer, but being Turing complete is an amazing property for mathematical systems that it's very rare to have. And Matthew Cook actually proved that Rule 110 was Turing complete back in 2004. And that reaches the end of the video. Thank you everyone for watching. I definitely didn't touch upon everything for elementary cellular automata, but I thought that these were the most important points. I may make a few follow-up videos expanding a bit more on Rule 30 and Rule 110, as I find these probably be the most interesting of all the rules. But yeah, I wanted to try something a bit different for this channel, so if you enjoyed, please let me know and comment any suggestions for future videos. Thank you for watching and have a nice rest of your day.